Salam and welcome everyone. So today we're asked to solve the question on the screen that says calculate the standard reaction entropy at 298 kelvins when 1 mole of nitrogen gas is formed from its elements in your reference states. So the first thing you have to note is that you're asked to find or calculate the standard reaction entropy at 298 Kelvin when 1 mole of nitrogen gas is formed from its elements. So 1 mole of nitrogen gas, so NH3, so not nitrogen, I apologize. 1 mole of NH3 gas, which is simply ammonia, is formed from its elements in their reference states. So we see that ammonia gas NH3 is comprised of two elements, and those two elements in the reference state is just simply nitrogen gas, okay, plus hydrogen gas. That reaction is what is going to give you ammonia gas, which is what we're asked to solve. So this equation is where we're supposed to this equation is what we're supposed to calculate the standard reaction entropy of. Now, I wanted to quickly mention something to you. This equation is not balanced, and we have to balance it in order for us to start solving for the standard reaction entropy. So, first thing you have to understand is this: whenever you're given a question like this, it's best for you to balance the chemical equation in such a way that you only have one molecule of NH3. So what this is telling you is this: you're going to write, or we're going to balance this chemical equation in such a way that we only have one molecule of NH3 gas, because this is the most basic form that we can have the NH3 gas, so that it's easy for us if we need to manipulate any of our work in future. So one molecule of ammonia gas is the same thing as having one one atom of nitrogen as well as three atoms of hydrogen. And in this particular situation, we have two nitrogens and two hydrogens. So we're just gonna basically like manipulate it with our understanding of how to properly balance chemical equation. So we need to have one atom of nitrogen on the left hand side as well. So what you just do is just turn this into half, because half of two is one. So now you've automatically balanced the nitrogen to also have one nitrogen on the left hand side. Now we're also going to do the same thing for hydrogen. Here we have three hydrogens. Here we have three hydrogens. Here we have two. Well, to go from three to two, you just have to have 3/2 here. So 3/2 times 2 is just basically 3. So that would be 3 hydrogens. So as you can see, you have successfully balanced. And that way to think about it is also in terms of decimal. Zero point 0.5 times 2 is 1, and then 1.5 times 2 is 3. So if you notice, we've balanced the chemical equation. So I'm just going to rewrite this balanced chemical equation as half N2 gas, okay, plus 3/2 H2 gas, okay. This is the balanced chemical equation plus NH3 gas. So this is what we're going to be using. Now, the next thing you have to note is this, because the work just started, is when you're asked to find the standard reaction entropy of anything, you have to remember the formula you're supposed to be using. The standard reaction entropy formula is simply the summation, okay, of the molar entropy of the product, okay, minus the summation of the molar entropy of the reactants. So what this looks like is that you are going to organize this chemical equation in terms of this formula. So we're going to have this: the molar entropy of the product, we know our product to be NH3 gas, okay? Okay, minus the molar entropy, of our reactant. The first reactant is N2, so the molar entropy of half N2 gas, because we're applying it to this particular equation, plus the molar entropy of the second reactant, which is just 3/2 H2 gas. So that is it. So the next thing you're going to do now is you're going to rearrange this in such a way that you make our work neater and easier to understand. So what this simply means is that we're going to bring out the coefficient that is not 1. Now, before we do that, I want to quickly say something. Remember how I have this V here and this V here. What this V is telling you is that this is the coefficient value for the products, or for each individual product. Okay, so this is a coefficient value for each individual product, and here you have the coefficient value for each individual reactant. So that's what this V here, and of course you see that the V here for the reactant is 1, so we're not going to pay attention because the coefficient of 1 is just 1. It's not like an interesting situation. As well as the coefficient here is half for the nitrogen and then 3/2 for the hydrogen. So putting that in mind, I'm going to reorganize our work. So we're going to have molar entropy. So just bear with me. If you've been watching my videos, you know exactly what I'm about to do. Okay, the molar entropy minus half, okay, times the molar entropy of nitrogen gas, okay, because that's how it's meant to be done, plus 3 over 2 times the molar entropy of hydrogen gas. So this is how the work is done. Now, the next thing you do after all of this is for you to simply substitute. And for those of you who don't know, all what I've been doing on my physical chemistry playlist is simply questions that are from the Physical Chemistry Atkins 11th edition textbook. And in this particular question, we use the resource section of our textbook, meaning the back of our textbook, to have the molar entropies of each one of the molecules. We do not Google it, we're not giving it in the question, but we know that we're going to use the resource section of our textbook to answer this question. So I'm just going to be substituting values from the resource section of the textbook. Anyways, moving forward, we have the molar entropy of nitrogen gas to be 192.45 joule per mole Kelvin, okay, minus 1 over 2 times the molar entropy of N2 gas is just 191.61 joule per mole Kelvin. Okay, that's 1. So this information here for now. And then you have the plus, because of course we're dealing with summation, plus 3 over 2, okay, times the molar entropy of H2 gas is just 130.684 joule per mole Kelvin. So that's it. So you have 192.45. So the molar entropy of, sorry, the entropy or the change in entropy of reaction is just simply 192.45, okay, joule per mole Kelvin. Joule per mole Kelvin, okay, minus half of 191.61 joule per mole Kelvin is simply 95.805 joule per mole Kelvin plus 3 over 2, or yeah, 1.5 times 130.684, or 3 over 2 times 130.684 joule per mole Kelvin. That would be plus 196.026 joule per mole Kelvin. So that's basically how it's done. So we have 192.45 joule per mole Kelvin minus 95.805 joule per mole Kelvin plus 196.026 joule per mole Kelvin. So that would be minus 291, okay, 0.831 joule per mole Kelvin. So the change in standard entropy of reaction will be negative 99.381 joule per mole Kelvin. Now, I want to quickly mention something to you. Anytime you're dealing with a physical chemistry question or just a chemistry question in general, you have to look at the proper number of sig figs as well as decimal places you're supposed to put your answer in. In this particular question, we have our values that we're using to be in um, 2 decimal places here, 2 decimal places here, 3 decimal places. In chemistry, we pick the value with the lowest number of decimal places. So we're going to have to put our final answer in 2 decimal places. So what we have is going to be negative 99.38 joule per mole Kelvin. Now, you would think the work is already done, but it's not. Let's go back to our question. We're told calculate the standard reaction entropy at 298 Kelvin when 1 mole of NH3, so of ammonia gas, is formed. We're told 1 mole of NH3 is formed from its element. So what this means is that we're going to multiply whatever our value is times the number of moles to be able to get our actual answer. So our answer here would just simply, the standard reaction entropy would just simply be negative 99.38, okay, joule per mole Kelvin times 1 mole. So cancel this out. Cancel this out. Just basically what we calculated had mole, and what we ended up getting as our final answer when we multiplied um the answer by 1 mole is going to be in just joule per Kelvin. So that's just the only difference. So basically what our answer is going to be now will be negative, okay, 99.38 joule per Kelvin. And this is basically the answer that we're asked to solve. If we're not told when 1 mole of NH3 is formed, and we're just so told when NH3 is formed from its element, we're not going to do the last process where we multiplied what we calculated for the standard reaction entropy by number of moles. We're just going to leave it as negative 99.38 joule per mole Kelvin. But since we're told, particularly when 1 mole, we have to multiply it, and then we have negative 99.38 joule per Kelvin. Hopefully, this has been easy for you guys to understand. If you have any questions, suggestions, or concerns, make sure you email me at yourhabitutoring@gmail.com, or just simply put in the comment section. If you're a student who is struggling in any of your STEM related courses, whether you're in middle school, high school, or college, and you're seeking a tutor, make sure you email me at yourhabitutoring@gmail.com. I help students succeed in all your STEM related courses and excel in academia. I also help students succeed through mentorships, basically whenever you're struggling or trying to improve or navigate school life. So yes, I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.